All right, hi everybody. Welcome back to office hours. New week. Today we don't actually have a warm-up that we're gonna do. We're just gonna jump into these chair conformer questions. So what we did on Wednesday last week is we took the whole session just to kind of talk theory. We went over a whole bunch of different techniques and trends and my tips for drawing these chair conformers. Again, just a disclaimer, like this is not how you guys are taught it in your actual class. It's just how I have learned to teach it, I guess, the easiest way over all these semesters. Like I think this is like the best possible way to do it. So, whatever way you like whatever way I guess suits you, you choose to do. But do you mind saying how far we are working through today? Caroline, I hope to get through all the chair problems. So probably hopefully through 40 maybe, something like that. Yeah, I hope to work through all those. So yeah, today's just gonna be like question heavy. We're just gonna keep doing practice. Stop me if you guys are confused at any point and let's try and get these problems good. All right, so the first thing you wanna do with chair conformers is you just number it any sort of way that you want to. There is no right or wrong way to do it. However, there is one that is always kind of better than the other. And by that, I mean, it's always best to have, some sort of substituent on 1 and 4, if possible, carbons 1 and carbon 4. And we kind of explained that last class. It's because 1 and 4 are the things that really move, while 2, 3, 5, and 6 are really the carbons that kind of stay in plane. So typically we'll number in a way to give 1 and 4 or one of those carbons some sort of substituent and, try to avoid 2, 3, 5, and 6. But if that's not possible, it's okay. There's no, I guess, penalty for that. So I see that I have a methyl right here. Maybe I'll call that 1 and maybe I'll number it this way. And literally that was just random. Notice how I definitely have something on 1. Even though I don't have anything on 4, like I definitely still have something on 1. So that's a good idea to start there. All right, so first thing to do is just draw your first chair conformer, okay? And I hope you guys are getting better at these. And the next thing you also want to do is you always number the carbons in the chair conformer. You can have these in your answer. I mean, I know you guys aren't doing a paper test, but I always number it. I always leave the numbers in there. It's just, it's important so that you don't like drop anything. Okay, so the next thing you want to do is you want to look at the stereochemistry. And when I say stereochemistry, I basically just mean wedge or dash. And you want to look at the stereochemistry of the substituent and see if it matches our trend. And remember, we said that wedges like to be up and dashes like to be down. So if your stereochemistry matches our trend, like we said last class, then we can leave it axial. So that's another thing I'll say. If the stereochem, which I'll abbreviate as SC, equals the trend, we said, let's leave that axial. And we said if the stereochem does not equal the trend, we made that equatorial. And these are literally all my notes on chair conformers, okay? So as long as you know that, I think you guys should be pretty good. Wedges typically like to be up. Dashes typically like to be down. The stereochemistry, if that matches our trend, and you'll see what I'm saying in a second by trend, then we'll leave it axial. If the stereochemistry does not match our trend, then we'll leave it equatorial. So on carbon 1, we quite literally pulled that above and on top of the plane. And that's kind of obvious of why we have this kind of pointy structure above 2, 3, 5, and 6. So 1 is oriented up. Does the stereochemistry on 1 like to be up? Well, yeah, we said wedges like to be up. So if the stereochem matches my trend, let's make that an axial group. So CH3. And by proxy, the thing that's not there, so this hydrogen, has to be equatorial. So there's nothing on 2 to consider, there's nothing on 3 to consider, there's nothing on 4 to consider, but now let's look at carbon 5. So what is my trend at position 5? Well, if we follow the up, down trend, it goes up axial, down axial, up axial, down axial, and 5 should be up axial. So that's my trend. It should be up and axial. So does the stereochemistry of the substituent on 5 want to be up based on the trend? And yeah, wedges like to be up. So if the stereochemistry matches my trend, let's make that axial as well. Okay, and then 6. So the trend on 6 should be up, down, up, down, up, down. So it should be axial down on 6. Does the stereochemistry of that substituent want to be down? Well, yeah, dashes like to be down. So if the stereochemistry match that trend, let's make it down. Okay, So you can see we have 3 axial substituents in this chair conformer. We have the 2 methyl groups above the top face of the ring, and we have that 1 hydroxyl group that's below the plane of the ring, okay? And if you guys look at the key might be slightly different with the positioning of these substituents. And it doesn't matter. That's why I said it doesn't matter how you number it, just as long as you have, for consistency purposes, 3 substituents adjacent to one another, and they alternate up, down, up. So if you guys are looking at a key or anything, you might see, 3 substituents adjacent to each other in that up, down, up fashion, but they might just all be moved, a little bit further along the ring. And that's okay. That's totally okay. All right. We're just looking for, do you have the right number of substituents in, the right relative order, and do they have the right orientation, all right? So then that's the first chair. We have to draw the next chair conformer. Okay, so I'm gonna draw this kind of like interconversion arrows. And let's draw the next structure. So now, instead of 1 being up, 1 is gonna be down, and 4 is gonna be up, okay? So this is my plane, 2, 3, 5, and 6, all right? And remember, we said in ring flips, anything that was axial always goes equatorial, and anything that is equatorial goes axial. And if you don't believe me based on that trend, you can just do the same thing, the same logic we did to get to that structure, matching the trends. But it's so much easier to see, okay, well now 1 should be axial down, and this was axial before, so it should be equatorial. Okay, so that was easy. That's how I got that one. And there's nothing on 2, nothing on 3, nothing on 4, but 5. So 5, it was axial up. So that means that CH3 group should now definitely be equatorial, and that hydrogen is now axial down, okay? And then on 6, so 6 we have said axial down, so then that should definitely be an equatorial group, and now that hydrogen is axial up. Okay, so if you look at this ring flip, what happened was we went from an axial, axial, axial to an equatorial, 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 okay? And now our task is to identify with a circle which structure is more stable. And it has something to do with what we kind of finished on, and it's called 1,3 diaxial interactions, okay? 1,3 diaxial interactions. And that might be a crazy term, but just think about it logically. 1,3 means on the 1 position, and then maybe the 3rd carbon removed. So 2, 3, so that would be this position, or 2, 3, this position. And diaxial meaning 2 axial substituents interacting. So here we have 1 axial substituent, another axial substituent, and those are going to interact because of their electron clouds. They're close by. So they're going to be interacting with one another. Yes, I saw that. Thank you. This should be hydroxyl. Thank you for that. Yeah, so essentially in this original structure, we see that we have 1,3 diaxial interactions on the top face, and we also have 1,3 diaxial interactions, which we can't necessarily see right now, on the bottom face. So there are these, axial hydrogens that are down, and then on the bottom face, we have these eclipsing interactions, okay? So there's a lot of 1,3 diaxial interactions, both on the top and bottom face of the ring or the chair conformer. But the minute we do this ring flip and we see that they become equatorial, we don't have axial groups anymore, so we don't have these diaxial interactions. So whenever we can put these big bulky groups on an equatorial orientation, we're going to definitely get a more stable chair conformer, all right? So that's how I would do these. Any questions on this question, I guess? Awesome. Caroline, go for it.
So when deciding which one is more stable, what should we, are we going to have that chart too? Or can we look at, which one would have more equatorial, as far as...
Yeah, great question. I think I know what you're saying. Some questions, they'll give you delta G's, some questions they don't. How do I definitively know? And in this question, in number 9, all of these examples, we're doing this very qualitatively. I've made these questions, which you may not see already, on purpose in such a way that you will always kind of see based on the number of substituents. There will be more in one of these ring flips that are equatorial than are axial on purpose. So you just basically, in these sets of questions, will pick the chair conformer, where you have more equatorial substituents. In the future, which we'll see, that's not really, this is a qualitative approach. When you really want hard data to know which one, the identity of those substituents will now come into play. And that's what we'll see. Oops. That's what we'll see. Where are my pages? Here we go. we'll see here with these charts, this is when we actually have to calculate because, maybe this is advice, maybe the amino group might be equivalent to a methyl group. Like we don't necessarily know. And that's when these values will come into place. So for these, we're just qualitatively kind of just seeing which one has more equatorial groups. And then we're going to build and actually use the delta G values to, see which chair conformer is the best. Okay. Does that kind of answer your question? Exactly. If you needed to use it, you would have it for the specific question. Like for 9A through F, you don't necessarily need them. So they're not going to be provided here. I'm going to do all of them. Don't worry. I'm going to do all of them. Yeah. Okay. Yeah. So for B, again, we're just going to number around the ring any given way. So I'm just going to pick this one to be 1 for this time. 4, 5, 6. Okay. Let's draw our first chair conformer. So we're going to draw it with carbon number 1 up and carbon number 4 down. So it's kind of like this lightning structure. If you guys like ever want something to like remember it by, like it kind of looks like a lightning bolt. Anyway, so on carbon 1, we pulled that carbon up. So the trend should be axial up at carbon 1. Does the stereochemistry of that substituent on 1 match? Well, yeah, it's a wedge. So that means we're going to have an axial up isopropyl group, and we're going to have this equatorial hydrogen. There's nothing on 2 to worry about, but there's something on 3. What's the trend for 3? Well, it's up, down, up. So whatever on 3 should be axial up. Does that stereochemistry of that substituent match being up? And no, we said wedges like to be up. So this is a dash. So if it doesn't match our trend, we want to put it equatorial. So this would be a CH3 group up there, and we're going to have an axial up hydrogen. Okay. There's nothing on 4 to worry about, but then on 5, our trend is up, down, up, down, up. So whatever on 5 should be up. Okay, so that's axial isopropyl, and that hydrogen is going to be equatorial. Okay, so that's really quickly how you're going to get the first chair conformer. Now, so Caroline, this might actually help you with your question. When you look at this one, we clearly see that we have 2 groups that are axial, and more specifically, both of those groups are pretty bulky. Like this is just a CH3, which is bulky in itself, but this is a CH with 2 CH3s. So you can see these are significantly more bulky and have significantly larger electron clouds in comparison to that methyl one, okay? So here we have 2 groups that are axial and 1 that's equatorial. So I think that can kind of give you some illusion into which conformer is gonna be better. So let's draw that next one for the ring flip. Okay. And number that around 1, 2, 3, 4, 5, 6. So that axial isopropyl group is now going to be equatorial, and that equatorial hydrogen is now axial hydrogen. Okay. Nothing on 2 to worry about. 3, the same situation. So down, up, down. So this should be now axial down methyl and equatorial for the proton. On 5, the trend is down, up, down, up, down. So 5 should be axial down proton and then equatorial isopropyl group. Okay, so something like this. You may not have them all in the same position, but as long as there's like a carbon in between each substituent and you have the right axial equatorial orientation, your chairs are going to be accepted. Okay, so now in terms of circling which structure is going to be more stable, let's think about the diaxial interactions. So before, we had the structure where these isopropyl groups are eclipsing with each other and the hydrogen on the top face of the ring. So look at all that significant diaxial interactions. But in this one here, we don't have the diaxial interactions for those isopropyl groups, but we do have them for the methyl, okay? So although we have diaxial interactions on the left and right side of this expression, clearly the right structure is going to be better or more stable because we have the 2 largest groups, the 2 bulkiest groups are equatorial, which outweighs the energy cost with this being axial. Does that kind of make sense? Like, yes, this one still isn't the best, but like out of the 2, it is better than that one. That's kind of what we're dealing with here, right? And we're doing this very qualitatively. We don't have any numbers yet. Okay, any questions on B? Cool. All right, so C, I hope you guys are just catching me with these examples. So I'm just going to call this tert butyl number 1, and that's good enough for me. So let's draw that first, chair. So we're up here, down there. So 1, 2, 3, 4, 5, 6. Okay, so 1 should be axial up. Does the stereochemistry match? Yep, so I'm gonna put tert-butyl up. I'm gonna go faster now. 2, the cyano group, that one should be down. The stereochemistry does not match. Let's make it equatorial. Okay. 3, the stereochemistry should be up. That stereochemistry does not match, so we're gonna make it equatorial as well. Done. Okay. You guys will get this fast. I know that was really, really quick, but you'll get that fast. It's just really quickly looking to see if the stereochemistry matches my trend. If it does, make it axial. If it doesn't, make it equatorial. Pretty easy. So in this chair conformer, we see we have 2 equatorial groups. We have this cyano group, we have this fluoro group, and we have 1 axial group, and that would be this tert-butyl group. So let's draw, the other chair conformer, this one. Okay, so quickly, what was axial becomes equatorial. Okay, so 2, that equatorial cyano should now be axial cyano, and that equatorial fluoro should now be axial fluoro. Okay, so something like that. So now we have 2 groups that are axial, and then we have an equatorial tert-butyl group. So this is going to be a question where you would need to have delta G values to be a little bit more specific, because now you can see, I don't know, is the cyano group worse than the tert-butyl? Like we don't necessarily know how repulsive those electron clouds are. But what I can tell you, at least up to this point, if you were to rationalize, let's maybe call this A and call this B, in the chat box, I said last class, something about what you always want to look for. It's something with one of those substituents. You want to identify the blank substituent, and you want that to be always in the equatorial position. Okay, so out of chair conformer A or chair conformer B, which one do we think? Somebody in the chat box, you guys can put A or B. What do you guys think? Okay, I see a B for Roxana, B for Abby. Yep, okay. So you guys are getting it. So B, yeah. Brian, great. Yep, great. You guys are all getting it. Okay, so yeah, so B is definitely the best one. And what I said last class was, we always typically want the largest, sterically hindered, bulkiest, whatever you want to use group to be equatorial. And you can kind of qualitatively right now kind of see the cyano group is 2 atoms. The fluorine is 1 atom, but this tert-butyl group is a lot of atoms. It's CH33. That's a lot. So because even though we still have, now 2 axial groups in comparison to my 1 axial group, this equatorial group being equatorial is so much more favorable because it's how significantly large that electron cloud is. So again, we're typically going to give you values, so you would know that. But right now we're just kind of introducing you qualitatively, like how to identify quickly, what would be a better structure. Okay, so C is definitely going to be this one. All right, so for D, maybe we'll see something different. I'm just going to call this 1 because I see it up top. And what I'm going to do is I'm going to draw the first chair. So 1, 2, 3, 4, 5, 6. Okay, 1 should be up. Nope, doesn't match. Okay, 2 should be down. Nope, that doesn't match. 3 should be up. Nope, that doesn't match. Done with the first chair. I'll give you guys a second to catch up. Okay, you see what I'm doing? Really quickly. I know it should be up, that doesn't match, so equatorial. That should be down, doesn't match, so be equatorial. That should be up, doesn't match, so be equatorial. Really quickly. It's just my cheat sheet way of cheat sheet or quick sheet? I don't even know. Whatever, one of those ways, one of those words, phrases on that to get you the right answer. Okay, so that's this. Okay, so then the other chair conformer, really quickly, 1, 2, and for you pre-professional people, you MCAT, DAT people that are eventually going to do this is how fast you have to be on the MCAT. Quickly draw 2 chairs, which one's more stable, really quickly, qualitatively, and then boom, you get your answer, So it's good practice for that. So what goes equatorial becomes axial, and what becomes equatorial is axial, and what's axial becomes equatorial. So 2 should be okay, so that's this chair conformer. So in the first structure, we had equatorial, equatorial, equatorial. Here we have axial, axial, axial. I think this is pretty much a no-brainer for which one's better. Obviously, we would prefer all of them to be equatorial. So in this situation, it's the first chair conformer. Okay. So now I'm going to leave E and F for you guys to do, on your own. I think we did 4 examples of those, pretty easy. So you guys kind of understand where I'm getting at now. You just want to get these pretty quickly. They're not so hard. And with the delta G values, they become a little bit trickier, okay? So any questions up until this point? Cool. All right, let's move on. And I'm hoping you guys are all good at Newman's by now and stuff. I don't think we need to go over those again. All right, so we're here. So this is a question that is really important. Everybody, listen to me. Know how to do 10 and 11. Really know how to do 10 and 11. Put a star next to them. Do whatever you got to do. I have seen these multiple times if you know where I'm going with that, okay? So know how to do 10 and 11. So for each molecule labeled A through E, decide whether the cis or trans geometric isomer would be a more stable chair conformer. And what the hell does that mean? Okay, so cis basically means same, and trans means opposite. Okay, so we kind of talked about, line angle. So what does that mean? So in line angle, we said trans, let's just say with respect to, the circled bond, the methyl group is on one side, and then maybe this ethyl group is on the other side of the bond. So this would be a trans arrangement, okay? But what is cis? So cis is like, let's say I rotated around this bond to get some sort of configuration like that. So with respect to this bond now, we have a methyl group and an ethyl group on the same side of that bond. So that's cis, okay? So that's what we kind of saw before with those terms. So how does that extend to chair conformer? And this is cis and trans geometric. We haven't necessarily got to geometric isomers yet, but it's this name, cis and trans, is exclusively reserved for, ready? Think about this term, di-substituted cycloalkanes, okay? So what does that mean? This cis-trans phrasing is only, used for di-substituted, did I spell that right? Di-substituted cycloalkanes, okay? So notice A through E, they are all cycloalkanes, cyclic structures, and they're all di-substituted. They all have 2 substituents, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, okay? So what does a cis, cycloalkane look like, and what does a trans cycloalkane look like? Well, a cis would be something like this. Maybe I have a wedged methyl and a wedged ethyl. And it could be any substituent, and it could be anywhere along the ring, just as long as they both are the same configuration. Whereas a trans, stereoisomer, a trans geometric isomer would be something like this. Okay, so how do I know that? Well, let's just think about the top face of this ring. Well, the top face of this ring has 2 substituents on the same side. They're both wedges, so that would be cis. And then here, one is up and one is below. That's kind of like this staggered kind of opposite fashion. And this would be trans, okay? So maybe that kind of now answers your questions about what is a cis geometric isomer, what's a trans geometric isomer. Cis just basically means all of those substituents have the same stereochemistry. Trans just means that they don't, they're opposite stereochemistry. And we want to know which one, either the cis or the trans version, would be the most stable chair conformer. And this is a very conceptual question. Okay, so you have to imagine what the chair looks like in your head, and you also have to imagine the trend, okay? So by that, let's think about this. So with letter A, let's call that carbon 1, let's call that carbon 2, okay? In my head, let's just say this is a wedge, and let's say that is a dash, okay? So now, in this chair conformer, in my head, I know carbon 1 gets pulled up in my first one, and then that should be axial up, and then in carbon 2, it should be axial down. So based on what I drew here in my head, I'm thinking, wow, that methyl group is gonna be up in the first chair conformer, and it's gonna be down for this hydroxyl group on the second carbon in that chair conformer. Okay, and if you don't believe me, I'm thinking this in my head. I'm thinking methyl is up, and I'm thinking hydroxyl is down. Okay, just from that orientation. And that's pretty unstable, right? That's pretty bad. But I know in my ring flip, those axial things are gonna become equatorial. So in my most stable chair conformer, which is when these 2 are equatorial, that arose from the fact that I made these trans. Okay, so I know I may have lost some people there, but I just was like, and this was just guessing, and you guys will probably guess too. Like, I just arbitrarily guessed that one was a wedge and one was a dash, like literally just out of thin air. And I was like, okay, well, the first chair conformer I'm thinking of in my head is the one where both of them are axial, following my trend. But then I know in my ring flip for this version, it's going to be equatorial. So that's a good thing. That's the most stable thing that I could possibly want. And the way that I was able to get this chair conformer in the first place was from making those substituents trans. That's why I wrote trans. All right, take a second for that to like digest. Anybody have any questions there? Abby, because if they were cis, the only one substitution. Exactly. Great, Abby, you got that. So it's a very, I think you can totally visualize it if you just said that, Abby. So that's awesome. It's like if they were cis, you know, we can show the opposite. One is going to be axial at a time, and one is always going to be equatorial, and that's not the best arrangement. So it's really just guessing and checking. Okay, and you take as much time as you need for these, like, you know, just try all combos until you figure it out. Like, you'll get there, you know. And Caroline, what's your question?
I think this was a way that Dr. Peterson, or maybe having it posted on like Piazza or something, but they said that another way to do this, which I thought was helpful, was so they said just to try drawing them both in the equatorial positions and then see like, is it going to be like up or down, or they're both up? Like, does that work too?
Yeah, it's just when you're just basically drawing a chair conformer where they're both equatorial. Is that what you're saying?
Yeah, so like drawing them and making them both equatorial, and then seeing like if they're both up or both down. And if they're both up, it'd be.
So my follow-up question to you is, how are you drawing it where they're both equatorial? Are you like assigning wedge and dash before, or you're just kind of going to a chair directly?
So I went to a chair directly, and then so I numbered it like 1 and 2, and so like the methyl would be like if the one's pulled up, then the methyl would have to be down to be equatorial, and then the second one, the hydroxyl, would have to.
Yeah, so you can do that. Yeah, that totally works. I see what you're doing there. I kind of just like this way because it's like guessing and checking, and like there's only like 2 combos, either wedge or, you know, wedge dash. Like it doesn't matter what you pick. So you'll know within 2 tries, you know, whether you get trans or cis. You might have more issues going to your chair directly because you have more chance to screw up there, like going straight to the chair. But either way, you can still get the right answer. It's up to you. You know, what do you agree with? What should we like more?
Thanks.
Yep. All right, and we're gonna do the next one. So B. So I'm literally gonna do the same exact thing. I'm gonna call this maybe a wedge just for fun, and I'm gonna call this one a dash. Okay. So my first chair conformer, I know this is gonna be axial, up, down, up. Okay. So if you noticed, this one is gonna be axial while this one is equatorial. Okay, in the first chair conformer. If you don't believe me, this is what I'm thinking in my head. And this is on 3. So up, down, up. So it should be equatorial CH3. So that's the first chair conformer. And I know in my ring flip, one is going to be axial again and one's going to be equatorial again. So that's not something I want. I want as many equatorial as possible. And I can make this equatorial maybe if I made this one a methyl. And you can see how then that's not equatorial anymore. It's actually axial. And then in my next ring flip, they both become equatorial in the ring flip. So clearly the cis version was better. Okay. Abby, what's your hack? I wonder if you beat me to it.
Okay, so I was kind of thinking about it because I already did a few of them. For A, so one substituent is on a 1 and the other one's on a 2.
Yeah.
And so it's 1 odd and 1 even number. So that one was trans. And then I also saw the same thing for C. One is on a 1 and one is on a 4. So that's 1 odd, 1 even number.
Yep.
And I said that one was trans.
Yeah.
And then for B, it's on a 1 and a 3, which is 2 odd numbers. And I assume that if it was also 2 even numbers, it would also be cis, but I don't know if that's right.
And Abby, you are a genius because I was going to tell you that after I did A through B. That is your
Sorry.
Yep. No, you got it. That's awesome. I'm happy you got there yourself. So exactly, when you see there's going to be a specific pattern, and you know you only have so many options you can tell, and when they're like on this 1 even number, 1 odd number, we can call that whatever, like that's always going to be trans, and the, you know, one, I guess the 2 evens or the 2 odds will also give you cis. Okay, so that is a way to memorize it. I hate telling you to memorize things. I think this is still, you should still understand it logically how to do it. But yes, you're totally right. And Caroline, yeah, I'll get there when I finish C, D, and E, and I'll explain it one more time. All right, so again, just arbitrarily pick both these to be wedges, or I don't know, I'm just gonna try the cis one first. So I'm thinking axial up, down, up, down. Oh, okay, so in that chair conformer, that would be axial up for the CH3, and then this bromine on 4 would actually be equatorial, okay? So that's not what I want, because one is always gonna be axial and one is always gonna be equatorial in either chair conformer. So the way to avoid that is to make, this bromine axial. So, with that dash, and it goes down, and I know in my next chair conformer, when I do the ring flip, both of those axial things will become equatorial. So this would be trans as well. All right, I'm gonna do it again on this one. So here, let's just call this wedge, and let's call this wedge. Let's try the cis one first. So that's 1, 2, and 3. So it's up, down, up. So you can tell that both these are gonna be axial up in the first cis conformer, and I'll draw it up here if you don't believe me. So it would be axial up for the ethyl, and then for 3, it would be axial up for the methyl. And you can tell in the next chair conformer, they'll both be equatorial. So the cis one will be best. Okay, and now I can use my shortcut. If you can tell if they are placed like in this fashion where there's one carbon in between, there's one carbon in between, it's the same type of pattern. Okay, so now I'm going to talk about what Abby said, and Caroline, hopefully this answers your question, is how do I know this trick? Well, whenever it's 1 with 2, or 1 with 4, or 1 with 6, it's always trans. So 1 with 2, 4, or 6, it's trans. Okay? If it's going to be 1 with, 3 or 5, it's cis. Okay? So notice it's 1 with 3, 1 with 3, 1 with 3. Okay? One odd number plus one. Yep, Abby got it. Abby's writing it down there. Okay? So that is a trick, like to always I guess fall back on and double check, but still know how to do it the normal chemistry way in the beginning. It's important. It's cool. All right. How do you guys feel about that question? It's typically always asked. So if you have any confusion, definitely ask it now. Okay. I honestly think just guessing and checking these chairs is pretty easy. Like it takes 2 seconds in my mind, but it's up to you guys. All right. So 11 is a little bit different. So this is basically saying in the more stable chair conformer, which we don't know what that looks like, how is the circled substituent oriented? Okay, and I just want to make a disclaimer now. Just because I see a wedge doesn't mean it's axial, and just because I see a dash doesn't mean it's equatorial. Same thing here. Does not mean that that's what we're doing here. What we need to basically determine is draw both chair conformers. Which chair is the most stable based on these delta G values? And in that chair, we're going to basically look for the orientation of the circle groups. Okay, so let me kind of show you what I mean by that. All right, so basically what that means is, let's just do this for A. So we have 1, 2, 3, and 4. And I'm going to draw, the first chair conformer, 1, 2, 3, and 4. Okay, and that one group should be up, and the stereochemistry likes to be up. So I'm thinking, ethyl group going up. 4 wants to be down, so I'm thinking that. Okay, so let's draw the next chair conformer after the ring flip. And again, I'm on letter A. And what happens with the axial group, it becomes equatorial, and that equatorial group became axial. And for 4, I think, oh, I'm sorry, that's not correct. For 4, we're here. Okay, so notice now from the left and the right, let's just say I don't really know what my delta G values are. Okay, let's just say I don't know anything about diaxial interactions. I'm confused. What I want to do with this chart is, what this says is the 1,3 diaxial, I don't know if you guys can see this, the 1,3 diaxial interactions for the ethyl group being in the axial orientation cost positive energy. Okay, remember positive delta G is not good. Okay, so it cost me 1.75 kilocalories per mole of energy to have this in the axial position. So I'm going to put plus 1.75. Okay, this hydroxyl group from being in the axial orientation also is going to cost me 0.93 kilocalories per mole of energy, because those are repulsive interactions with the other axial protons. We have an axial proton here, we have axial protons here, and they eclipse with one another. So essentially, that adds up to, let me get my calculator. Sorry. Okay, so that's 1.75 0.75 plus 0.93, that's going to be 2.68. Okay, so this is positive 2.68 kilocalories per mole of chair. Okay, so one chair, so we just, for all intents and purposes, this chair on the left is positive 2.68 kilocalories per mole. Okay, so then what's the values over here? Well, over here, when the ethyl groups and any of these groups go to an equatorial orientation, we actually have negative energy because we're free. That's what Gibbs free energy is. We're freeing up this tied up energy. That's the whole concept. You know, when they say what's Gibbs free energy? Well, it's tied up here, locked in this, axial, repulsive, state. And by putting them on this equatorial fashion, we actually free up Gibbs free energy. We're freeing up the Gibbs energy. So instead of it being plus 1.75, it's negative 1.75. Okay, that's a good thing. We just saved all of that energy. And then this hydroxyl group, we saved this energy. So this chair conformer is negative 2.68 kilocalories per mole. Okay, so clearly when delta G is, a negative number, we are spontaneous, or we prefer to go to the right side. So we know that this is my more stable chair conformer. And then now we look to the question. Now the question says, for this this circled, substituent, how was it oriented in my most stable chair conformer? And in my most stable chair conformer, it was equatorial, excuse me. Okay, so we would write equatorial for this, question. Okay, and it's not always that obvious, and you'll see that with B and C. Okay, so you guys kind of follow what I did? First, you draw both chair conformers. Then you identify which one's the most stable, and then you look in that most stable chair conformer to find out what the orientation of that substituent was. Okay, so let's try B. I'm gonna just maybe flip this over. That's true. I thought when we go from equatorial to axial, it is positive. Yes, so what is the question? We did do that. So you can, use this logic. These are all the equatorial positions. And if you go to the axial position, you go from the negative numbers to the positive numbers. And that we did see that. Okay, cool. All right, so for B, I'm just gonna call maybe this one 1. I literally don't care. It doesn't matter. So 1, 2, 3, 4, 5, 6. Okay. So on 1, that stereochemistry doesn't match. So I'm thinking this. 2, nothing. 3, nothing. 4 should be down. So that's okay going down. 5 should be up. So that's okay going up. Okay. So that's my first chair conformer. And then I'm going to draw my next one. So I'm just showing you guys how fast you guys will get at some point. So, what became equatorial is now axial. There's nothing on 2, nothing on 3. 4, that was axial amino. So now it's, equatorial amino. And 5 was axial methyl. So now it's equatorial methyl and proton going down. Okay, so here's an exact example, a perfect example of where you actually need these delta G values. And here's why. So if you look, we have 2 axial groups over here on my left chair conformer. And we have 1 axial group here. But is the big, isopropyl group being axial, better than these 2 groups being axial, even though they're smaller? See, so we don't know. Clearly 2 axial is worse, qualitatively than 1 axial. But the identity and how big those steric clouds are kind of actually comes into play here. And that's why we have these values. Okay? So let's just calculate our energy values. So in our left chair conformer, that methyl group being in this axial orientation, where's methyl? It's supposed to be 1.74 kilocalories of energy. That's bad. So this cost me 1.74. Okay, that's bad. And then that amino group being axial cost me 1.41. That's also bad. But then this, not terpidyl, this isopropyl group is equatorial. So that's negative 2.15. That's a good thing. So if I sum up all those numbers, my energy, my Gibbs free energy for the left chair conformer is going to be 1, positive 1. Okay, so that's positive 1 on the left. So on the right side, we have the amino group being equatorial, so that's freeing me up negative 1.41. The methyl group is freeing me up negative 1.74. But that isopropyl group being down is now positive 2.15. Okay, so let's add those all up. And now you get a G value of negative 1 kilocal per mole. So out of the left and the right, structures, we see that the right structure is going to be the best one because we have a lower set of delta G numbers. And how was this isopropyl group oriented in this most stable chair conformer? Well, it's axial. Okay, so you see, typically you always say, like, you want to say equatorial, 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 but that's not necessarily true when other substituents are there, because sometimes, even though this is like axial, it's the lesser of two evils. It's better being in that orientation than the two methyl and amino groups being up. Okay, let's see. Not that the calculations are super difficult, but we'll be like, we're gonna give you easy numbers, Leah. We don't, like, I know these are like decimals and stuff. I feel like you can do these by hand, honestly, like, adding, 1.75 plus 0.93, you can really do it. But I think the numbers will be easier. We'll probably give you like half numbers, like 1.5 or 2, or I made these up too. Like, I literally just made these up. Like, we don't really care that you memorize any number, okay? But definitely no calculator on the test. Yeah, sorry. Okay, so C, let's try C. Actually, I'll give you guys a second. You guys try it, and I'm gonna do this. So while you guys try it, I'm gonna make a poll. And I'm gonna make a poll for you guys real quick. Let's see if I can do that. All right, guys, I hope you guys are trying this one out. All right. All right, so does anybody want to walk me through what they did and take a stab at it? Or C, anybody want to try? I'm gonna call on someone randomly. No, like, oh, please don't be me, please don't be me. And I'm scrolling, and Madison, do you want to take a stab at this?
Sure.
Yeah, it's all good.
So you draw your chair.
Sure.
And then you draw your substituents.
Okay.
Like based on how you numbered it. So I started with the tert butyl as 1.
Okay.
And then I went counterclockwise.
So you went this way?
Yes.
Cool. Okay.
So then on my chair, I started in the top right hand. Yep, exactly.
Awesome. Okay.
And then I put my substituents on there based on the wedges and dashes. So 1 was up, axial.
Perfect.
3 bromo is equatorial.
Awesome.
And then same for 4 with the fluoro.
Perfect.
And then I drew the second chair.
Okay. Awesome. And how did you do this with this? Yeah.
Yep, I flipped the axial and equatorials.
So you got, was that 3? Yep, so it should be that, and 4 should be that. Okay,
And
is
then
that what
I
you got?
started doing the G values, but I didn't finish them.
Gotcha. Okay, well, that's perfect. So you basically have like all of that right. So hopefully everybody was following. Thank you, Madison, for volunteering. Or I kind of didn't let you volunteer. I kind of just picked on you. But let's just do these delta G values. So that terp butyl group is up. That's plus 5 kilocals per mole. Okay? Plus 5. Like you can just tell why that's such a big value because of the CH3, 3 configuration. So it's plus 5. The fluoro and the bromo are just singular atoms. So that's why they're all the way down here with, minus 2.4 and minus 0.57. Here, those are going to cost me positive numbers, and that's going to be negative 5. So I don't really even need to calculate this for you guys to really see. The fact, this is plus 5. So no matter what, this isn't even adding up to 1. So we're going to be around like plus 4, on the left, something around there, plus 4-ish and change. And then here, you're going to be negative 4 and change. So clearly the right structure is better. And how is that terp butyl group, aligned? And that's clearly equatorial. Great. All right, and those are, how I do these questions. These are probably the two hardest, like most conceptual questions. I haven't really seen anything asked more difficult than this. So if you guys know these are pretty good shape. All right. I guess the last thing we can do is just talk about KEQ and equilibrium. And you guys kind of know that at this point. Yes, so negative delta G is favorable. So Madison, just back to like what Gibbs free. I think they skipped over this in freshman chemistry, like what they told you guys. But no, it's not a stupid question. Oh, different question for Leon. Essentially, Gibbs free energy is like how much energy like a system has. And you want to have like the lowest possible energy because that's just the most stable. Like we'd like to be grounded, We go back to that lightning example that we talked about in the beginning of the semester. Like lightning is extremely, charged. It's not stable, and it is so loud and reactive because of that. So we like to be, grounded and have a nice even distribution of charges, and that makes it stable. So in this situation, when we're freeing up that energy, and that's denoted by the negative value, like we're freeing it up in space, like we're giving it off, that's a good thing. That means that my structure is overall pretty stable. And that's kind of what we want. Negative delta G's, and that corresponds to positive KEQ. And we're going to see that here. Okay. And that was your question, but does it matter which group you number first? Absolutely not, Leah. Thank you, Abby, and everybody else for answering. Yeah. All right, thank you. All right. So 12. So here, all we want to do is like do the ring flip in the chair, and this is pretty easy because the templates have been given to you. So it looks like this is my maybe 1, and that was my 4, and this is my 1, and that's my 4. So that's kind of important. So that equatorial isopropyl group is now going to be my axial isopropyl group. Okay, and that I guess axial ethyl group on 3 is now going to be my equatorial ethyl group, and we have an axial proton. And on 4, it was axial fluorine, but now it's going to be equatorial fluorine and axial proton. Okay, so that's really all I did was, in terms of, filling in this chair conformer. I'll write little A, E, E, so you guys understand that. And here it was E, A, A. Okay, so in the left, we have axial isopropyl, so that costs me positive 2.15. These two ethyl groups being equatorial are going to be negative 1.75 and negative 0.26 respectively. So if I were to add up all those numbers, the left side is positive 0.14 kilocals per mole. And then on the right side, this is going to be negative 2.15, positive 0.26, and positive 1.75. So 1.75 plus 0.26 minus 2.15 is going to give me the negative version of that. Okay, so delta G is always, I guess you could say delta G is always, products, minus reactants. So we could say delta G equals negative 0.14 minus the 0.14, and then you get negative 0.28. So your delta G of your reaction is negative. So that's all we need to care about is the sign. And we say that the delta G of the reaction is negative, which means it's spontaneous, which means it prefers the products, which means that your equilibrium lies to your right. And when we're estimating the value of KEQ, if we favor products, you remember KEQ equals the products over the reactants. If there are more products, KEQ should be greater than 1. Okay, so we would say in this example, the equilibrium lies to the right with a KEQ value greater than 1 because delta G, I guess we could say, is less than 0. So these would be like all the things that you want to be able to deduce from this problem. Equilibrium lies to the right because that's the more stable chair conformer, which means our KEQ is going to be greater than 1, which means our delta G is going to be less than 0. Any questions on those like thermoterms and equilibrium terms? Cool. All right, let's try 13 and we'll be done. So again, let's just I guess this will be, what time is it? This will be like one of our last problems that we do today. Ayana, what do you mean by that? How do you act? I just showed you how you calculated it.
So like I was doing this like earlier and I was like looking at the solutions because I was confused. And it says like KEQ is like 1.27. So how do we actually get like that 1.27?
Oh, you don't have to. Excuse me. Sorry. I'm getting a FaceTime call always at this time. Sorry about that. So I'm sorry about that. I just lost my train of thought. Yes. So I see. So there's a formula, and you're not going to have to do this on the test, but the formula is delta G equals negative RT ln KEQ. Do you guys remember that maybe? Some of you guys from Gen Chem? Is this sideways? Sorry. There we go. So this is the formula. So R is the gas constant. So that's 0.0821 L dot ATM over mole Kelvin. T is your temperature in Kelvin, which we don't have. I guess you could assume room temperature. So maybe like 298 Kelvin. And you would have to do the ln of KEQ. And again, you're not going to have a calculator, so you're not going to do this on the test, if that makes sense. But that's where she's getting it from. Okay.
Oh, okay. Thank
All
you.
you need to know is the sign, and you would be able to know KQ is greater than 1, even though she said 1.27. If that makes sense.
Gotcha. Thank you.
Yep. Anybody else have questions on that or the theory? Okay. Cool. All right. So let's move on to one more example of this, and let's just fill in the template up top. So what's axial is equatorial. Actually, let's number this. So that would be 1 down here and 4 up here. So that axial tert-butyl is now going to be equatorial tert-butyl. That this is on 3, so that equatorial phenol is going to be axial phenol. So remember that's phenol. I'm sorry, phenyl. It's a benzene, and that would be here. And 4, that it looks like an isopropyl group, and now it's axial. Okay, so it looks like, in terms of our ring flip, we go axial, equatorial, equatorial, we go equatorial, axial, axial, just to confirm. In my left structure, axial tert-butyl cost me 4.90 kilocals, phenyl cost me -3, and isopropyl cost me -2.15. So if you were to add up those numbers, it's going to be 4.90 minus 2.15 minus 3. So I actually got -0.25 kilocals per mole on the left. If I were to do this on the right, I see that I have positive 2.15, -4.90, and -3. So -4.90 minus 3 plus 2.15 is going to be -5.75 kilocals per mole. Okay, 5.75 kilocals per mole. So in this case, did I do something wrong here? One sec. Equatorial becomes axial, and that becomes axial. Should be +3. Ah, thank you. Yes. I was like, something is not adding up here. Yeah, so this cost me +3, this cost me +2.15, and then -4.90. So that gives me, thank you, that gives me +0.25. I was like, something is not adding up. Okay, so yeah, they should always be the same sign, just opposite. Okay, so essentially, I can see that delta G on the left is going to be, negative. So this is clearly the more stable one. So what does that mean? So delta G here has to be greater than 0 because we favor the the reactants. And that means for my KEQ that I'm actually going to be less than 1 in this example, which means my equilibrium lies to the left. So all 3 of those things can be determined. Delta G is greater than 0 because it's not spontaneous. You're not going to go to these products. KQ is less than 1 because you favor your reactants, not your products. And your equilibrium is going to be favoring your reactants, all for these reasons that we talked about. Right? And I'll leave C and D for you guys at home. Let's just talk briefly about what's coming up. So this is the end of chapter 2 material, chapter 2 in your textbook, I should say. And we are now going to move into chapter 3 in your textbook, or chapter 4 in the student workbook. And that pretty much after this chapter, or this section 4, you know, in the workbook, that's the end of your exam 2 material. So where are we at right now? So I told you guys we would, you know, come back to this. We have isomers, which is really chapter 2. I'm sorry, is it chapter 2 in this workbook? I think it's chapter 3 and chapter 4 in the student workbook. And isomers, we said there are 2 types. There are the ones that differ because of connectivity, and those are constitutional. And so we said that there are some that differ in 3D arrangement. Okay. And we are getting into the first type of 3D arrangement differences, and this is due to 3D space. Okay, rotation. I should say rotation and 3D space. And we have 2 types that we've seen so far. We've seen Newmans. So those would be like, you know, maybe this versus that. Those are a type of isomer of butane. And we've also seen now chair conformers. So we've seen, you know, that versus that. These are definitely a type of, you know, rotation in 3D space. So we've kind of finished up this branch, we finished up this branch, and then the rest of chapter 4, I guess, in the student workbook is going to be called differences in chirality. And I think you guys are kind of already starting there. So differences in chirality is going to give rise to our next 2 main types, and then that pretty much sums up isomers for you guys in Orgo. Okay, so we'll finish that on Wednesday. I think we'll pretty much get through all the chapter 4 material for the most part, and you know, you guys will be golden. We can just keep doing practice. Does anybody have any other questions before I sign off?
I had a quick question on stereoisomers.
Sure.
So when you have 2 shared conformers, how do you determine like which ones are stereoisomers?
I'm sorry, say that one more time.
When you have 2 shared conformers, like how do we determine, like, is it up and down and then equatorial and axial? Like what lets us know that they're stereoisomers?
Just like, for instance, like if we just look at this example, these are stereoisomers of each other. Like the ring flip is the stereoisomer, if that makes sense. Because what's happening is here, you're rotating bonds and you're getting a new structure that has the same chemical formula but differs in some way. So this would literally be a conformational isomer of each other. So you're just looking for the axial things to go equatorial and the equatorial things to go axial.
Okay, that makes sense. Thank you.
Yep. Anyone else? While I drink my coffee. All right, I'll see you guys on Wednesday. Good luck, everybody.